5 pi over 6. Well, it's easy to check. It's easy to check. Thanks, guys. 5 pi over 6 is definitely a number that lies between 1.57 and 3.14. So I think that's good. And does it have a sign of a half? That yes, then I think you can't possibly be wrong. Yeah. Sabrina, what about the next one? Pi over 6. And again, on all of these, we're relying. There's a reason we do this only after having thought a little bit about speed trig values. We're relying a little bit on your knowledge there, that you understand, that this is one of the special angles, pi over 6. That lies in this interval, and it does have a cosine of root 3 over 2. So I think we're doing well. Matt, what about that part C?
C.
Pi over 2. Pi over 2 has a tangent that's undefined, I think. There's definitely a pi involved somewhere, though. You want to fix it? What'd you say? 3 pi over 4. So 3 pi over 4 is between 0 and pi. And that has a tangent of -1. Do you guys agree with that? John? How do I keep John? 5 pi over 3. Do you guys agree with that? I'm going to write it down and then I'm going to think about it. Let's see. 5 pi over 3 is between 180 and 360 degrees. And the secant is 2, or the cosine is a half. Okay, so I think I'm good on that. Any disagreement with any of these up here? Oh. All right, thanks, guys. All right. This is going to be a helpful set of problems, a good foundation for what we're going to do today, which is our last lecture of this unit. We're going to talk about inverse trig functions a little bit. And we're going to do a little activity tomorrow, Wednesday, ID problems, Thursday, review, and Friday test. So you might be thinking already, you guys did not talk over me, sorry, I'm really losing voice. We've already talked, you might be thinking, oh, didn't we just do inverse trig functions on Wednesday? Isn't that what we're doing? Feels like that was inverse-ish. But be careful. Remember, by inverse, we mean inverse with a capital I. We mean inverse, like as in the first unit of this year, we mean F inverse. Like the function that takes, instead of x to y, y to x, right? We mean inputs become outputs, outputs become inputs. That inverse, right? So we're going to start by doing the inverse sine function. And keep in mind that, in fact, what you were doing with the warm-up just now is inverses, right? Like I gave you the output values, didn't I? And you had to come up with the angles which gave you that output. So you've already had a little bit of a thought about this. So let's start by graphing sine inverse, and the way that people write that is one of these two ways. Your calculator uses sine inverse with this to the negative first notation, which is a little bit unfortunate. And then we can also use this arc sine notation. Either one is fine. You should know what both mean. Now, I'm thinking about inverses here, so I'm going to go back to like kind of my algebra 2 style approach to how I think about inverses. Here's the original function, and I'd like to, from it, construct an inverse of this function. Well, right away, I think you have enough experience in like thinking about this. An issue. What's the issue? It's not 1-to-1. I love that came out right away. Yeah?
It's not a function.
Yeah, sine is a function, but if we take the inverse and show the inverse relation, which we could do, we know that that won't be a function. So what can be done? Yeah, here. Okay, yeah, so we could pick a piece that, I think I hear you saying we should restrict this somehow, and that's correct, right? We should restrict the domain somehow so that when we do the inverse, we get something that is 1-to-1, right? We get a piece that is 1-to-1. So that's what we're looking for. We're on the hunt for some domain restriction that will produce a 1-to-1 function. And right now it's not. So, suggestions. What did you say, something about half a period or something, Peter? All right, where though? What piece? Where? So like from 0 to pi. It's a sine graph, but I mean this is actually the y-axis here. It's hard to tell, but
if you go from the max to the min, whether it's sine.
Yeah, from a max to a min, like from here to here, he says. Do you see this? What he's saying? And by the way, what criteria are you using to like figure out which piece is going to be 1-to-1? How are you finding that?
Horizontal line.
Yeah, you're thinking about the horizontal line test. I mean, something you haven't maybe thought about is like, how do we know that a function is 1-to-1 just in general? Like that's hard to figure out. I mean, you have the horizontal line test to apply visually. But like if I just hand you some random, like, I don't know, say like I hand you a cubic function, you know, I don't know, x cubed minus 2x plus 4.
And you already put it in.
Is that 1-to-1? I don't know. I mean, some cubic functions are 1-to-1 with no adjustments needed. And some, that one I think actually isn't. But how would you know? I mean, maybe you've never thought about that question. What criteria would you have to think about? What would you have to use? What are you looking for in the picture? I don't know. Yeah. Okay. I mean, again, you kind of like have to think about it visually. Yeah.
If there's more than one input or output, that's the same.
Yeah, but that's like, how do you know for the cubic I just gave you that that's true? I don't know. I mean, it'd be an interesting question. How do you figure out whether a function is 1-to-1 without like? I mean, I guess you could look at the picture, right? And that's about where we are in life. Maybe I don't know. Yeah. 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 There is something else I could say there too, but I think that's good enough. So what piece do we want to use? Well, Peter's piece is a good one, but it's actually not the one that mathematicians use usually. We usually use this piece right here, and again, this is the y-axis right here. So what are the edges of this yellow box? The x coordinate. What are the x? What is the x range here? The domain, the restricted domain.
Negative pi over 2 and
Yeah, you should know the max and min of a sine curve. All right, I'm gonna. Everyone, look at my cute baby. All right, sorry for that brief interlude. Okay, sine inverse. Are you ready to graph it? The domain of our restricted domain is negative to positive pi over 2. So that tells me what?
dumbest thing I've ever.
That tells me what about the inverse function, sine inverse? Negative pi over 2 to pi over 2 is our domain for sine. What is that? Yeah, that's the range of sine inverse, right? So I'm gonna put arbitrarily, how about, I don't know, we'll call that pi over 2 right there, how about? And we'll call this negative pi over 2. That's the range. The domain of sine we're taking now to be negative to positive pi over 2. And that will be the new range of sine inverse. What's the domain of sine inverse over here? Negative 1-to-1, because why? Because that's the... That's the range of the original function. So I'll just put it there and there. I don't know. I'm just picking a spot randomly. All right, negative 1, 1. All right. So let's do it. Are you ready? Sine inverse of, let's start with 0 because it's easy. What angle has a sine of 0? 0, okay? Or you can think the point 0, 0 is on the original sine graph. So the point, switch the coordinates, 0, 0 is on the graph of sine inverse. Okay. What's the sine inverse of negative 1? That is, what angle has a sine of negative 1? Yeah, negative pi over 2. And what angle has a sine of 1? That is, what is sine inverse of 1? 1. All right. Now, I know a lot of you would like, when first asked, what is an angle that has a sine of negative 1, you know, you might say 3 pi over 2, right? I think some of you might go for that one. But you have to acknowledge that negative pi over 2 is a valid response too. And so what happened to 3 pi over 2? Well, let me just show you where the rest of this goes, right? Right, so if you were to have plotted the entire inverse relation, it would look like this, right? Does that make sense? And we're only choosing to show you this piece. If we were to show you even a little bit more, it would fail the vertical line test, right? So we're not showing you anymore. But I will tell you that this point right here, it has the coordinates -1, comma, 3 pi over 2. So some of you might have wanted to report that. That's because maybe you wanted to pick this piece. I think that's actually the piece Peter suggested originally, which would have worked perfectly well. It's just what mathematicians haven't agreed on, you know. So, all right. Feel free, by the way, to graph this on your calculator to get the same picture. Okay. By the way, I should say this should explain again something we actually have had this conversation already when we were doing like solving triangles and all that, and we were using sine inverse on the calculator. Do you remember us talking about that? And I told you, hey, when you use sine inverse on your calculator, we'll only output values between negative and positive 90 degrees. Yeah. Do you remember that conversation?
Yes.
So here it is again. Yeah, Ananya.
So like if we were like asked to graph sine inverse on like a test or something, would we only graph that piece or like?
Right. That's.
Can we choose any piece?
No, sine inverse we only mean just like the square root function. It's not any piece of the inverse parabola that we choose. We just decided we all agree on it's the positive square root, right? The principal square root. So same here. We've all agreed that this is what we mean. Even though you're right, it's completely arbitrary. It's completely a mathematical convention. It's not like a part of the universe, right? It's our, yeah. I said it's not a part of the universe.
No, it is a part of the universe because we've decided it's part of the universe.
Oh, okay. Well, that's fine. Yeah. Yeah.
So does it have like a period?
No. No, not periodic. All right. Inverse cosine. Let's do the same process. Here's a little picture here. Again, here's the y-axis. Can someone tell me a good piece to use here? Again, we want to use the same kind of criteria. Yeah, I think it's pretty clear here. What do you say, Teo?
I could use the max that's on the y-axis and then the mean to the right.
Right, which is actually what Maddie just said too. It's 0 to pi. There it is, 0 to pi. And I think we're ready to graph it. So the domain restricted on cosine is 0 to pi, so that's our new range, like we just talked about. So here's 0. I don't know, here's pi. How about? And what's the domain again for cosine inverse? It's still just like the last one. Negative to positive 1. So I don't know where you want to put those. How about here? And here it doesn't really matter. Okay, and now we're ready to plot some points. So what is the cosine inverse of 1? That is, what angle has a cosine of 1? I think it's always helpful to say it that way, isn't it?
Yeah.
Cosine inverse of 1. Wait, what do you mean? What angle has a cosine of 1?
Pi.
0. All right. What angle has a cosine of negative 1? Yeah, it is pi. Negative 1 is the cosine of pi. And what angle has a cosine of 0? What's cosine inverse of 0 is what I'm asking. What angle has a cosine of 0? Pi over 2. So 0, comma, pi over 2.
Oh.
Okay, and make sure you get the concavity right when you do this, right? Do you understand why I curved it the way I did? It's not just that I want it to be decreasing for you. I want it to be decreasing with the correct concavity. And how do you know that? Well, because if you were to continue this, it would look like a cosine curve, right? Right? So, some of you might be tempted to draw it with like a slightly different concavity. Just make sure that it would make sense if you continued it. Does it look like the cosine curve and it's inverse graphically? You should. Okay. Again, we're only thinking about this one piece though. And again, do you remember thinking about this? Actually, again, we've had this conversation, haven't we, a little bit before already when you use the cosine inverse button on your calculator? At one point I just told you, your calculator will output the value only between 0 and 180 degrees. Do you remember that?
Yes.
I said your cosine inverse will always give you a value between 1 in the first or second quadrant. Yeah, I just kind of told you that, but now we've had a little bit more of a discussion about why that's true. Okay, you can graph this on your calculator. I would encourage you to think about the relationship between this graph and the last graph, too. In what sense are they the same or different? Could you transform one into the other via a sequence of rigid motions? Yeah. I think you could. All right. let's talk about the inverse tangent. All right, same process here. Here's a picture of tangent off to the side. Again, the y-axis is right here through the middle. Tell me a good piece that you might want to choose for this one. Yeah, the central thing. Yeah, absolutely. I think it's pretty natural. I think we would all agree that that's a pretty clear choice for us. So what's the restriction on the domain? What did we just pick? From what to what? So what is the domain? It's negative pi over 2. The restricted domain will be negative pi over 2 to pi over 2. The open integral, right? That's a little different. Okay. So here we go. Let's put
because it can't touch.
pi over 2 and negative pi over 2 on our graph.
Oh, this is
And what is the domain of tangent inverse? Yeah, it's actually the whole real number line, right? Isn't it all reals is the domain, since the range of that little blue box picture there is all reals. So must be the domain of tan inverse. All right, so that's cool. Let's start plotting some points. Tan inverse of 0.
0, right?
Yeah, the angle has a tangent of 0 is 0. What other inverse tangent values do we know? Tan inverse of 1, I like that one too, yeah. Let's put 1 here, how about, I don't know. What is the tan inverse of 1? What is the tan inverse of 1?
Pi over 4, right?
It is pi over 4, yeah. And the tan inverse of negative 1, while we're in the area?
Negative pi over 4.
Negative pi over 4. All right, and that's 3 points. Tell me what else you know. What else is going to happen here? Yeah, horizontal ones. All right, are you ready? I don't know how good I did there, but yeah, something like that. How do you like that? I mean, really, tan inverse is surprising. You might have been like thinking, like, it's a little bit cumbersome, a little awkward on sine, cosine. It's only getting worse. Actually, plot twist right here. Tan inverse actually is beautiful. Turns out to be really nice. Domain is all real. It's nice, smooth, beautiful curve. So that's cool. I like that. It actually turns out to be super useful in lots of instances too. It's not. It might seem like the stuff we're doing here is like not that interesting.
Wait, are we going to do inverse?
Comes up a lot in probability. There's a probability distribution that has that uses this a little bit, and comes up in calculus a lot actually too. Yeah.
What's the difference between this?
They are similar because they both have horizontal asymptote. You're astute to notice that. Yeah. But I think you'll find they have a little bit of different behavior, and there isn't really a way to transform one into the other. But you're right to notice. It's like we now have 2 functions we can point to that have 2 horizontal asymptotes, and that's cool. Yeah. All right. Thanks, guys. Yeah, so that's the inverse tangent function, and that brings us
I
to
saw this is what I was doing.
the multimedia portion of today's lesson.
I remember this episode. Great episode.
You know, I am a fan of ventriloquism. Maybe you, me, and your dummy could go get a hot beverage. He can talk while you drink. Nope, want to watch some watch.
I love where he talks.
This appears significantly more.
All right.
Do we have to draw this?
All right, let's, yeah, I mean, we will do, I forget what the homework is you do in graphing of these, but we definitely can do some simple transformations of those too. I'd like to just do a couple problems where we're just simply, right now, simply evaluating some of these. I want you to evaluate these keeping in mind the restrictions that we've all agreed on in the mathematical community. So by sine inverse of 1/2, I know that there are an infinite number of angles that have a sine of a half. I'd like you to give you the one that we said, though, that we would agree on. That is, we said sine inverse is only going to output values between negative and positive pi over 2. So don't think too hard here on this one. What is that? Yeah, not a trick question. What about the next one? Again, think about cosine inverse. What did we agree on that cosine inverse would output? And then answer the question, what angle has a cosine of negative root 3 over 2 that's in that range that we agreed on? Do you agree?
But you said it became pi over 3.
I mean, a lot of you might say 7 pi over 6, or I mean, a whole host of an infinite number of other options. But 5 pi over 6 is the one that has a cosine of negative root 3 over 2 and is in between 0 and pi. Right? And that's what we need. We said we would only output values between 0 and pi. How about tan inverse of negative 1 over root 3? Again, keep in mind the range we agreed on for tan inverse. Yeah, what do you think, Lisa?
I know what we were just doing, but you just
Yeah, I mean, this was, you could like point to this place on the last graph we drew, right? Negative 1 over root 3. Anyone? I don't think that has a tangent of negative 1 over root 3.
It's 2 pi over 3.
Anyone have it? What'd you say? I don't think I've heard the answer yet.
What is it?
It's negative pi over 6. Yeah. All right. So I heard some of you say. I heard some of you say 5 pi over 6. 5 pi over 6 does have a tangent of negative 1 over root 3. But we said that tan inverse was going to output values between negative and positive pi over 2. We just drew the graph, didn't we? We said the range for tan inverse was going to be negative to positive pi over 2. Okay? Again, that was an arbitrary choice, but we agreed on it, so we should obey the thing we agreed to. I realize there are an infinite number of things that do have that tan inverse. Some of you also said negative pi over 3. I can't really help you, okay? That's just not right. Okay. That doesn't. I do understand that. And then the other thing that some people get confused on is they might say 11 pi over 6, because tan inverse outputs values in the first and fourth quadrant. So, got it, 11 pi over 6. But by the range of tangent is negative pi over 2 to positive pi over 2. I mean, the range of tangent, of inverse tangent, is negative 1.57 to 1.57. Remember, these are numbers. And is 11 pi over 6 a number that is on the number line that lies between negative and positive 1.57? No. Right? I know they're coterminal, but that's not good enough. Okay? Yeah? No. Is that right?
Yeah.
All right. All right, now they get interesting. Talk to me about D. Now, pi over 9, I don't know the sign of that. I do know how to draw it, though, right? Here's the sine. Here's pi over 9. If this is 1 unit long, then this is sine. I have pi over 9, right? This distance right here. Right? So what is the angle that has a sine of pi over 9? Sorry, yeah. Did anyone say it? Don't overthink this either. What is it? It's pi over 9. All right, now we need to be a little bit careful here. We need to be a little bit careful here because we're right here. Because a lot of you are thinking, oh, this is just f inverse of f of x, right? It's inverse composition rule. We just get back the input we did. It's like the stapler and the unstapler thing, right? Staple remover. But just be careful as we go forward, as we think about this, because remember, sine and cosine can accept an infinite number of arguments, right? But arcsine doesn't output an infinite number of arguments. Let's go on to the next one. So cosine of negative 1.1 Again, I'll draw a little picture. Negative 1.1, by that I mean negative 1.1 radians. So I happen to know that that looks like this. I don't know much about it, but I do know it looks like that. Negative 1.1 radians, somewhere in there, right? Let's assume this is 1 unit. All right? The cosine of negative 1.1 radians. Well, that's this distance right here. Oh, excuse me. This distance right here. Right? This is the cosine of negative 1.1. That's the distance along the x-axis there. All right, now I have to ask you, what is the cosine inverse of cosine of negative 1.1 of this distance? What angle has a cosine of that? Certainly negative 1.1 has this as its cosine, right? Because I just drew the picture. But can we output negative 1.1 as an answer? So what angle does have a cosine of the same thing? It needs to have the same cosine. This, whatever this is the cosine a positive number, it appears to be. What angle can we output that has the same cosine? Yeah, how about 1.1? Is this an angle that has a cosine of negative 1.1 too? This has the same cosine. 1.1 does, but now that's actually a radian measure we can output, isn't it? Because cosine inverse returns value between 0 and pi radians. Okay? You can't output negative 1.1. Cosine inverse just doesn't do it. Even though negative 1.1 and 1.1 have the same cosine.
What's the answer to the next one?
Yeah. All right.